to Jasper for inviting me to talk here, and obviously to the Potters for enabling such an exciting event. What I'm going to do in my talk is essentially try and paint the larger picture around global change, and key drivers of global and to some extent regional change, and how that feeds through into thinking about ecological and biodiversity change. And I hope that I'm going to leave space for the other speakers, Pip and Jasper and Dieter, to actually say something much more interesting, which is actually about what you do on the ground at the scales at which ordinary people live and operate. So this is kind of context within which and background for something much more interesting that I hope to follow. So I would start off with a couple of sets of graphs. These are graphs produced by an Australian guy called Will Steffen. And he pulled together data on, first of all, socioeconomic trends around global socioeconomic trends. And if you look at all of those graphs, essentially they're showing the changes in a particular index from the pre-industrial era through to roughly today, at least to the year 2000. And all of those dark grey curves are ramping up, increasing over time as we go from the past to the present. And this is true for a range of socioeconomic indices. So we can look at population growth, traffic associated with that, even McDonald's restaurants, large dams to supply that growing population. Every single index relates to socioeconomic growth, and everything's trending in an upward trend. So the next question that he then looked at was then, well, what's happening in the Earth system, as we call it, to global environmental trends, so indices of environmental health, etc. And we can look at an extremely similar graph for a set of graphs for a range of different environmental indices. Some of them will be very familiar to you. So carbon dioxide emissions, natural disasters, coastal ecosystem health, temperature trends, and the topic of this talk, biodiversity indices. All of those trends are essentially impacts on the natural environment, on the Earth system, are showing very strong similarities to those socioeconomic trends. And that's no surprise. They're highly correlated, and in fact, we can actually go beyond talking about correlation and talk about causation. In many of those instances, there's pretty much unequivocal evidence that these environmental trends we see are being driven by those socioeconomic trends. So we can put a direct link that's pretty much beyond reasonable doubt that atmospheric CO2 concentrations are caused by fossil fuel burning, and that those concentrations are producing the observed trends in global warming. So what we're seeing are these trends in environmental stress, if you like, and what I'd like to do next is move on to talking about what this actually means in terms of ecology. So one aspect of the environmental picture that this global change is driving. Perhaps to finish off by just mentioning this term, which might be familiar to many of you, but Will Steffen and Paul Crutzen, who was the Nobel Prize winner, who did all the original work, some of the original work on the loss of the ozone hole, has termed this change in environment that we're seeing as something called the Anthropocene. And for those people who understand sort of long-term geology, we've come through a number of geological epochs. So, and most recently the Pleistocene, which is a sort of a period of ice ages, leading up to a period of about 18,000 years ago, when we shifted into what's the current warm period between ice ages, called the Holocene. And they've coined this term the Anthropocene, which is essentially saying we're now moving into a geological period where the overriding geological signature that we'll see in geological records is actually the human imprint on the natural system rather than natural processes, which is what's been happening in the past. So essentially we're now sort of entering into an experiment in the Anthropocene through this coupled social, ecological, environmental world that we're now living in. That's very different to anything that the Earth has experienced in the past, since about 1850 or so, with the onset of sort of rapid industrialization. Okay, so what I want to do now is focus on 3 areas where global change is really acting as a big driver on ecological systems. The first of those is climate change, and this is where I know a little bit, and I can talk with some authority. The second 2 relate to a cause of climate change, carbon dioxide, but that actually directly affects ecological systems as well. And then finally, a global pattern that has very local impacts, and that relates to land use change. So let's start with climate change and step back once to look at this, probably one of the most iconic geophysical records around, which is the record of atmospheric carbon dioxide concentration from the Mauna Loa Observatory on top of one of the mountains in Hawaii. And that's showing us just this remarkable trend of increasing carbon dioxide. And we know we can prove that increasing trend by various chemical analyses. That trend is indubitably caused by fossil fuel burning and burning related to land use change, so deforestation. We cannot hypothesize another source for this carbon dioxide. So what does that mean? Well, it means that from a climate change perspective, we are producing an enhanced greenhouse effect. And the enhanced greenhouse effect means warming over and above the natural levels of greenhouse gases in the atmosphere. What this has caused up to now is a global warming, and in fact a warming over South and Southern Africa, of about 1 degree above pre-industrial temperatures. So this graph up to the present day is responsible for a planet Earth that's already 1 degree warmer than without human activity on it. What does it mean going forward in time? Well, that depends a lot on society, obviously, and what happens to future emissions. But we can think of a number of different possibilities, and that's shown in that top graph for temperature change over South Africa. So the brown section of the curve is what we've experienced. That's the climate risk that we've already caused. And those colored graphs show potential climate change depending on what happens with future emissions, from a medium-high emissions pathway to something slightly lower. Now, what happens in the future is partly cast in stone because of the inertia in the energy system. We're already committed essentially to another degree of warming that we can't avoid. And that's just emissions that are going to be happening over the next 10 or 15 years, and there's just no time to change the world energy system to switch out of the fossil fuel economy. Beyond that, it's all in play. So if the international negotiations really take off and do something fantastic and we get the best possible outcome, then we might be able to limit the future warming to somewhere above an additional 1 degree over the 1 degree we've already experienced. If things go pear-shaped, we could be looking at 6 degrees warming by the end of the century, and if we follow what's probably most likely, then we're probably in 3 to 4 degrees temperature warming by the end of the century. So all bets are off there, but the climate change issue is really one of a future risk. We've got an emerging climate change risk, and the really sort of worrying thing, I think, is that every gram of carbon dioxide each of you emitted getting here is going to be hanging around in the atmosphere on average for the next 50 years. So what you did getting here has a legacy that's going to last for the next 50 years. And this is a real problem in the climate change arena, because actions now actually have their worst impacts way into the future, and humans, as well as economists, people are very good at discounting the future and weighting current. It's kind of delaying gratification for the opposite. Buy now, pay later, rather than pay now and buy later. Anyway, but just to put that in context, I just took my own family and sort of thought, well, where are these impacts going to play out in terms of the lifespans of people that I know and care for. So my parents are quite old. If they live for another 10 years, that'll be a bonus. So 2020 is about for them. My wife and myself, hopefully, if we're healthy, we're going to be like my parents in about 30 years' time, thinking about retirement villages, etc. My children will be my parents' age, maybe in the 2060s. My grandchildren haven't been born yet, are probably going to still be alive at the end of the century. So all of the decisions that I as an individual am making are actually going to play out to people in my family that I know already or will come to know and love in the next 10 or 15 years. So I think that sort of puts a nice reality check on how we think about both personal actions, individual actions, but also the politics that we want to engage in terms of thinking about climate change specifically as a driver of environmental change. So what do those sorts of climate changes mean in the Western Cape? Well, here's one example. This is showing, on the left, the current distribution for a particular plant community, essentially a landscape. And this is the succulent Karoo landscape, semi-arid succulent Karoo landscape. And everywhere that's black are environmental conditions where, in the present day, this particular landscape can occur. That's what we call an environmental or climatic envelope that controls the distribution of that. And dark black means much more likely to occur, and as you go to lighter greys, less likely to occur. As you move forward in time, using a middle of the range scenario for what climate change will do, so 2050s when, if I'm lucky, I'm still alive, then we've got a range shrinkage due to climate change of approximately 50%. And if we go right out to the end of the century, global warming of somewhere around about 3.5 degrees over pre-industrial levels, so middle of the range, a range shrinkage of maybe somewhere in the order of 70%. So that's essentially what the direct climatic impacts on a whole biome, if you like, could potentially be just due to one of these drivers, which is climate change. The next thing I want to talk about is another aspect of the fossil fuel burning issue. This actually relates to the direct impacts of carbon dioxide on vegetation communities. So here's an example of a grassland somewhere in, I think it's in Lesotho, but it's showing this mix of grass and shrubland. And the interesting thing about CO2 is that it has two direct effects on vegetation. It has what we call a fertilization effect, which is because plants at current levels of carbon dioxide, actually photosynthesis is limited by CO2 concentration, so it's a limiting factor. So if you increase carbon dioxide levels, CO2, carbon dioxide, becomes less of a limitation, and all else being equal, plants can actually photosynthesize more for a given chunk of air that they suck in through their leaves for the photosynthetic process. So what that means is that as CO2 goes up, plants could potentially photosynthesize more effectively and faster, but the interesting thing is that different plants respond at different rates. One of the big contrasts is between grasses and trees and bushes. And trees and bushes have a much bigger response than plants. And one of the interesting signals that ecologists are seeing over a lot of southern Africa, over grasslands, is woody encroachment. They're called woody encroachment to areas that were previously grassland. And there's a strong hypothesis that this is actually, at least in part, driven by a CO2 fertilization effect. This is a direct effect of global environmental change, actually reorganizing existing ecosystems. Here's an example of how this has actually been quantified. This is for a grassland area in the Eastern Cape that has been a conservation area for many, many years. And all of the red dots, the red little circle or squares, show areas of that grassland that have switched from grassland to scrub and forest land. So we're looking at something like 30 to 40% shift since the 1930s. And this is estimated using repeat historical photography. So we're seeing changes that we can't prove necessarily are due to the CO2 effect, but it's our best hypothesis out there at the moment. And that hypothesis is actually supported by some really amazing experiments that colleagues of mine, William Bond and other the people in the botany department and also Guy Midgley at the South African National Botanical Institute have done, where they've actually taken different tree species and subjected them to experiments, these artificial CO2 experiments. So this is for the species of acacia, one of the common trees that actually is involved in this woody encroachment. What they've got here are examples of roots from these acacia at different levels of carbon dioxide. So on the far left, a root from an acacia that's grown for exactly the same period of time, under exactly the same conditions of moisture and temperature, but at glacial CO2 concentration levels. So carbon dioxide levels in the last glacial period, which are at about 180 parts per million. And then sequencing to the right, 260 parts per million, that's pre-industrial levels of carbon dioxide. 375, that was ambient, present-day levels of CO2 in about in the 1990s, and then some future scenario of 540 parts per million. If you look at those roots, there's a huge difference in the biomass that's been built up due to this fertilization effect. So the hypothesis here is that CO2 fertilization effect is producing much stronger seedlings that are actually much more able to establish themselves in the landscape. And then when the normal factors like fire and grazing come and attack these trees, they're actually able to withstand that and reach maturity much more easily. So we're seeing dynamic changes in the landscape, probably driven by these CO2 changes. If we go to the marine ecosystems, there's marine, particularly coral reef systems, are hit by this double whammy of temperature and carbon dioxide as well. On the temperature side, we have these coral bleaching events, where if temperature goes above a certain threshold for a certain period of time, the coral organisms expel the algal zoo, whatever they're called, zoo thingies. That's those zoo thingies. Anyway, the algae which provide the nutrients, they expel them, and they provide the colour and the nutrients to the reef-building organisms. And if that happens, if that bleaching occurs for a certain period of time, of more than a few weeks, and with increasing frequency, then the corals can't recover, and essentially you get a collapse of the coral reef ecosystem. At the same time, we have CO2, carbon dioxide, being drawn down into the oceans, absorbed by the oceans, and increasing ocean acidity. And all of these reef-building organisms use calcium carbonate to make their skeletal structures. And what happens when you increase acidity, the calcium carbonate starts dissolving. So as fast as these organisms try and build their skeletal structures, it's being dissolved by increased carbon dioxide in the oceans. So coastal ecosystems are also being subjected to quite serious change. And if you speak to people who are in charge of management of the Great Barrier Reef, they're basically planning for a future without a Great Barrier Reef. That's their planning scenario, their conservation scenario at the moment. Okay, finally, briefly moving on to landscape. I don't know if anybody can recognize where this image, courtesy of Google, is, but it's part of Cape Town, and that dark patch is the Belleville Hills, whatever they're called, the hills above Belleville. Yep. So this is the sort of landscape change that we're seeing over South and Southern Africa. The only bit of possibly natural vegetation left is that dark band of the Belleville Hills. So everything else is a transformed landscape. So if we think of a driver of ecological change, in fact, human use of the land is probably the main factor affecting ecological change at the moment. The climate change issue is the emerging risk that's overprinting onto land use issues. But that's a key driver. And it doesn't only affect the areas where land use is changing. If you look at invasive species, this is essentially this is a map of invasive species in catchments around South Africa, and all the red areas are where there's high levels of invasive species. And these are species essentially that have escaped from areas of converted land use and invaded so-called protected or conserved areas. So you're seeing essentially leakage and externalities from human land use actually affecting the so-called natural environment as well. So where does that leave us? There are at least three big drivers of ecological change that I've mentioned. They're not the only ones, but they're really quite significant. And what we really need to think about is how do we manage that? And how do we actually decide what is sustainable, what is a level of ecological consumption that is actually sustainable? And that's quite a hard question to answer. One way of thinking about it is this idea of an ecological footprint. So this is work that isn't without its controversies, but essentially when people talk about ecological footprint, they will calculate the resources, the biological resources that are used, that are needed to produce any particular thing that an individual, city, a nation consumes. And then they work out the area of land that consumption actually uses in terms of active biological resources. And then they look at the waste side of it. So what area of land is required to actually process the waste products as well. And you can come up with an ecological footprint for an industry, a country, a city, a household. And this shows national statistics of ecological footprint. And the key thing to first of all look at here is this horizontal line here. And that's the average ecological footprint in hectares per person for all available biologically productive land on Earth. Okay? So that's including protected areas. So that's, if you like, the maximum threshold. And then if you look at all of these dots, that's where different countries are sitting. So obviously, as we'd expect, the USA is sitting up there in probably a totally unsustainable manner. South Africa sits over here. We're already above our global ecological allowance, if you like. And then most of the rest of Africa, all these brown dots, is sitting down there with a low ecological footprint. But what we've also got to think about is human development. And particularly in the African context, there's a development imperative. The average standard of living is very low, and this is reflected along this axis here by one of many indices one could use to describe well-being at the nation state level, the Human Development Index. And as you'll see, most of Europe and some of Latin America and the Middle East is sitting to the right of this value of 0.8, which is some sort of threshold for a decent standard of living. And then the rest of the developing world is sitting to the left. So the challenge we have is essentially we have a finite ecological resource that the planet can use. Globally, using some estimates, we are using 1.5 planets at the moment in terms of the ability of the planet to renew in a sustainable manner that ecological footprint. This shows the national picture. And the challenge is to essentially get into this little, very small quadrant over here, which is a decent standard of living, an HDI of above 0.8, and an ecological footprint that essentially is within the capacity of the Earth to actually deliver it. So what does that mean? Well, it means the United States has got a heck of a long way to go. There's a cause for Great Depression. South Africa's actually got quite a challenge because we're sitting at with a Human Development Index of around about 0.7. It's been stuck there since 1994. It hasn't changed. But we're already above that threshold. And we have one of the highest, what's called Gini index, disparities in wealth, across South Africa as well. So we've got big problems. What about something like Niger? They've got a long way to go. And what we want to really do is keep them on a horizontal path. Because if every African and low-income country follows this kind of path, then we going to deplete those resources beyond a sustainable level until in getting to, we haven't got room to claw back that ecological footprint. So, in summary, where does that leave us? I think maybe a little bit depressed, initially. There's a big challenge out there, and I think there are three things we need to think about in trying to meet that challenge. First is about efficiency. much of that ecological footprint is due to inefficient processes. So, for instance, 30% of food that's produced is never consumed. So we could reduce the agricultural footprint by 30% if we were more efficient. You can think of that through all sorts of different processes. The second relates to, I think, what I would call replacement or alternatives. So on the carbon side, there are alternatives. We can go to renewable energy. There are alternatives that don't carry a carbon footprint. And maybe in some of the other ecological aspects of ecological footprint, there are alternatives. But that's not going to solve everything. And then the final one is actually about individuals and people and consumption. What is a sustainable level of consumption, even if we are highly efficient and have all the latest technology? And for an equitable distribution of that ecological resource, there's going to have to be a shift to more sustainable basic levels of consumption. Because we can't all turn into Americans. We can't even all turn into the average South African, because then we are already over that threshold. So we have to find ways of consuming that's different to the way we consume at the moment. Thank you.